Lesson 2.1, Relations and Functions. This set of notes is closely tied to the activity that we did in class with domains and ranges and matching graphs. The goal for this lesson is to be able to represent relations in various ways and identify the domain and range of a function. So there are several key terms to be looking out for in this lesson: pairing, relation, function, domain and range, vertical line test, function notation, independent variable, and dependent variable. So here's the key concept. We can actually represent relations in 4 different ways. We can list out the ordered pairs, inputs and outputs, x's and y's. We can do a mapping diagram where we list all of the inputs in one bubble and the outputs in the other, and then match them up based on our ordered pairs. You can see that the arrows show how to pair each input with an output. So 4 is actually paired in this case with 2 different outputs. We can make a table of values, an X or input column and a Y or output column, matching the inputs with outputs. And then finally we can make a graph where we plot the points on an XY coordinate plane. So the domain of a relation is the set of inputs, also called x-coordinates, of the ordered pairs. The range is the set of outputs, also called y-coordinates, of the ordered pairs. And a function is a relation in which each element of the domain corresponds with exactly one element of the range. So each x value can only be matched with exactly one y value. So here's an example. When skydivers jump out of an airplane, you can see pictures here, they experience free fall. So the photos show various heights of a skydiver at different times during free fall, ignoring air resistance. How can you interpret, or how can you represent this relation in 4 different ways? And you can see the times. So at time 0 we have our skydiver in the airplane at 10,000 feet. And then at time 4 seconds he has fallen down to 9,744 feet, and then we have his different times and heights listed. And those are all plotted on this graph. You'll notice there's a break in the graph because there's a jump from 0 to 5,000. So we can represent that with this zigzag line here. So let's go ahead and start off with listing out the ordered pairs. So our ordered pairs would be we can make one of our squiggly braces like we did for our domain and range. Our ordered pairs would start with 0, 10,000. We could put a comma in there, not to be confused with the comma separating our input and our output. 0, 10,000, followed by, we have 4, 9,744. Then we have 8. It looks like the time frame is going up by 4 seconds each time. 8,976. Then at 12 seconds, we're at 7,696 feet. And lastly, we have 16 seconds. Looks like we're hitting the water here. 5,000, or maybe the ground. Nope, we're still near. 5,904 feet above ground. So at 16 seconds, we're at 5,904 feet. And close that off with a curly brace. So that's representing our relation with ordered pairs. Next, we could do our mapping diagram. So we've got kind of our, we might make a bigger bubble, a bigger oval than that, just to give us space here. So this is our mapping diagram. And we'll list out our inputs. I'll just label those underneath. Inputs over here on the left, outputs on the right. Inputs would be these x values, 0, 4, 8, 12, and 16. And then we have 10,000, 9,744, 8,976, 7,696, and 5,904. And in this case, we just draw our arrows. There's exactly one output for each input, so that does make it a function. And then finally we could make our table of values with our inputs or x values and our outputs or y values. So again, we would list out our inputs 0, 4, 8, 12, 16, and then our outputs 10,000, 9,744, 8,976, 5, did I skip one? No. 7,696 and 5,904. And those are our 4 different ways to represent a relation. Next, we'll try to determine whether each relation is a function. So again, going back to our definition here, a function is a relation in which each element of the domain corresponds with exactly one element of the range. So each x can only match up with one y. So -3 only matches up with 1, 0 only matches up with 1, so this does work out. This is a function. A is a function. B, we see 4 is matched up with -1. Let's see if there's any other 4s. There is another 4 matched up with a different output. So already we can see that this is not a function. Part C, looking at 2 here, is matched up with a -3 and a 3. So already we see this is not a function. Turning over the page, you can use the vertical line test. Vertical line test is another way to be able to determine whether a relation is a function if we're looking at a graph. The vertical line test states that if a vertical line passes through more than one point on the graph of a relation, then the relation is not a function. And you can see here's an example to the right. Our vertical line hits in 2 spots. This is not a function. I'm gonna pull out my lead here because it's a little narrower than my pencil itself, so you can see when I line up my vertical line with my graph, it hits in more than one spot. So A is not a function. B, when I line this up, there's no point. Let's see, is there? Nope. None of my x values is matched up with 2 different y values. It passes the vertical line test, so this is a function. And then C, you can see does not hit in more than one spot at any given time. So again, C is a function. So A, not a function, I'm going to abbreviate. B is a function, and C is a function. Then a function rule is an equation that represents an output value in terms of an input value. So you can write a function rule in function notation. So let's take a look here. The inputs are x values. So the outputs are the y values. So you actually read this as f of x equals 3x plus 2. Or when we plug in a value for x, we would say f of 1 is the output when 1 is the input. So the independent variable x represents the input of the function, and the dependent variable f of x represents the output of the function. It is called the dependent variable because its value depends on the input value. So let's look at a couple more examples here. For f of x equals negative 2x plus 5, what is the output for these three inputs? So go ahead and work these out. First plugging in negative 3 for x, f of negative 3 and then we simplify. So negative 2 times negative 3 is positive 6. Negative times a negative is a positive 6 plus 5, which is 11. Then we'll try f of 0. Substitute 0 in for x. Negative 2 times 0 is 0, so 0 plus 5 is just 5. And finally, f of 1/4, substituting in 1/4. Negative 2 times 1/4, so you could write that as a fraction. Multiply numerator times numerator, denominator times denominator, we get negative 2/4 plus 5, which simplifies to negative 1/2. Negative 1/2 plus 5, so that's like saying 5 minus 1/2, which is 4 and 1/2. And our last example for this set of notes for this lesson, talking about ticket prices. So if you're going to a concert, it's a very practical example here. Ticket prices for a concert available online. The tickets are $35 each. And then there's, of course, a shipping and handling fee, and it's $2.50. So the total cost is a function of the number of tickets bought, the number of tickets. What function rule models the cost of the concert tickets? Evaluate, so we'll figure out the function, and then we'll evaluate when we have 4 tickets. So let's first define a variable t as the number of tickets. And you can see here it says total cost is a function. So let's make our function c of t. And then we'll substitute in the values that we have. $35 each indicates that depending on the number of tickets, we'll be paying $35 per ticket. So 35 times t. And then no matter what, we have to add on that $2.50 shipping and handling fee. So that's how you would rewrite this scenario as a function rule. And then it says to plug in a 4, substitute in, or calculate the cost of 4 tickets. So we're going to substitute in a 4 for t. So 35 times 4 is 140 plus 250. So our total cost there for 4 tickets is $142.50. So we saw a lot of different terms there, but they all relate to one another. Starting in the front, we saw our inputs and outputs in 4 different ways to represent a relation. We saw ordered pairs and a pairing of those numbers. We saw domain and range, the set of inputs and the set of outputs. We did the vertical line test here on the back. Used the vertical line test to determine whether a relation was a function, whether or not it was a function. And then we talked about function notation, where instead of writing y equals for our output and input, we wrote f of x equals, and represented our output stayed an x, but the y became this new expression f of x, which is just a little bit more efficient way of writing our function.